Hey, good morning, everybody. Good afternoon, good evening, whenever you're watching this video. This is Mr. Sheeline, and we are going to be going over the Unit 2.1 notes covering two-dimensional motion and vectors. Okay, so let's just get right into it. No point in holding back. Or at least let's just a quick brief update. Remember, we just took the Unit 1 test, and the Unit 1 test covered one-dimensional motion. And remember that one-dimensional motion is pretty much just motion on a straight line. So on a single axis, whether it's the x-axis or it's the y-axis, doesn't really matter. It was just on a single axis, going back and forth, going forward, going backwards, whatever it was, going up or down. Now we're going to be working with things. We're going to be adding a second dimension. So we're going to be going in, say, one direction. We're going to go to maybe, say, to the right, and then we'll maybe go up, and then we'll go to the left, and then up again. So we're going to be adding all kinds of different directions, and we're going to learn how to navigate through this, calculate it, and we finally get to use some actual trigonometry. Okay, so recall. So the difference between uniform motion and non-uniform motion, it's just this little review. Remember, uniform motion is the movement at a consistent speed in a straight line, whereas non-uniform motion means movement which changes in speed or direction or both. So it's important to understand these two terms, these two seemingly simple and straightforward terms. Uniform motion was, for the most part, what we worked with. In one-dimensional motion. There were some questions that we had, like, for instance, a guy throwing a ball up in the air and it falling down to the ground. There was one about your dog walking in the park. There's all kinds of different examples that we looked at where you had instances of uniform motion. And then some instances where you had non-uniform motion. So a good example of that was the Bugatti. So the Bugatti Chiron video. In the Bugatti Chiron video, there's acceleration. And because there's acceleration, that's a change in velocity. And a change in velocity is a change in speed. Okay, and we saw that. So, but now, for the most part, we're going to be working with a lot of non-uniform motion. Most of it is non-uniform motion because you're changing direction all the time. Okay, so we're going to be looking at that, and it's important to understand the distinction between the two. Okay, all right, vectors. So vectors involve a magnitude and direction, and we understand this. We remember this. Vector quantities have both magnitude and direction. But what we're going to be working with is obviously vector quantity still, but with vectors. Okay, and what are vectors? Well, for the most part, vectors are these little arrows, these little lines that we use in order to indicate distance, to indicate velocity, to indicate direction. I have some in my nose, sorry. So as an example of a vector, 100 kilometers per hour to the east, you would draw this would be drawn as a horizontal line with an arrow pointed in the intended direction. However, most movement occurs at some combination of the horizontal and the vertical, so meaning it's not all in a straight line. It's possible that we're going to be moving in, to the southeast, to the northwest, to the, whatever it may be. And we're going to get into, in just a bit, we're going to be getting into how we can know which one's which, or how to best categorize it, I guess, maybe a better way of saying it. Okay, so as an example here, you could say that there is you would have a vector showing something moving at 100 kilometers per hour, which is roughly about 50 miles per hour, a little less than that though, but 100 kilometers per hour in the direction 50 degrees south of east. Okay, and it would be drawn with an arrow pointed east but directed 50 degrees down. Okay, which is a great description, but we're going to go into that into a little bit more detail. But first, we have to look at vectors and their specific anatomy. Now, I'm not going to really test you on the anatomy of a vector, but what I am going to be testing you on is that when I ask you to draw a vector, it pretty much better look like these guys. So, and something I just realized I don't have in the notes, but we'll go over in the how to draw a vectors demo when you come back to class. But let's just go through with kind of the anatomy of a vector. So one of the first things you have here is you've got the head. So the head of the vector is just obviously this guy up here. It's your little arrow. Okay, and it's super important to draw your vectors. And again, we'll go over this in class, but it's super important to draw your vectors as best as you possibly can. And you have to make a distinction between the head of your vector and basically the dotted end of your vector. Okay. Oops, I got to do this. Okay. You also have the tail. Okay, now the tail is more or less just more like the shaft, if you want to call it. If it's something like, if you want to actually think of it like an actual arrow that you would shoot from a bow, this would be the shaft. It's not the tail end. It's just the shaft of the vector, and it's number 2 there. It's the length of between the arrow and the dot. Okay, and just because I've never been able to find any kind of source material that talks about the end dot of a vector and gives it a name, I just call it a dot. I've called it an origin before. More or less, the dot, and again, we go over this in class, but the dot here, this is the start. This is your start position. Oh my goodness. This is your start position, and this is pretty much your end position. Okay, for the most part, right now, that's what you need to know. The dot is your starting position. Your head is the end position. Okay. All right. So typically a compass as well is also made when you are drawing vectors, since it's not always obvious that up is north. So and on top of that, it not only helps a reader, but it helps you. So if you have a word problem that talks about going in a particular direction, and then another particular direction, and then another particular direction, it's a good idea to have a compass handy, because you're probably going to be referencing that compass, or you might be drawing on that compass. Okay, so typically, again, when we're using vectors, at somewhere on your paper, somewhere on your worksheet, there should be a compass. Am I going to grade you to have a compass? No, but you should have a compass. You should have one available, and it should be there ready to go for you to reference. Okay. So when you look at a vector, you can break it into its horizontal and its vertical components. Okay. So here's thinking about this. So this is more or less putting together the direction of a vector. So northwest vectors both have a northward and a westward part, and any upward and rightward vector is going to have an upward and rightward part. So it's more or less just saying, like, use your compass, use your brain, and just and know that yeah, something that moves diagonal from left to right. So meaning it looks like this guy. If it looks like this guy down here, it looks like him down here. You're going to have there's going to be an up, and there's going to be a movement to the right. Okay, and that's important because that's how we break these vectors down, and that's how we can calculate if we don't know. Let's say we don't know what this guy is. If we don't know what this guy is, we can use this guy, and we can use the information with this guy to solve for this. Okay. We're going to use good old trigonometry, which for the most part right now, it's basic geometry that it's probably been a couple years that you've done, but this should, come back to you pretty quick. Okay. Oh, and that's supposed to be by paragraph, but whatever. So now, because we break these things down into their X and Y components, we then have to be clear about the specific direction they're heading. So we've got to figure out how we write that. So we must use a compass to accurately label our headings. Using the picture provided, we can use this to tell us the specific position. So this 50 degrees south of east was not supposed to be in there, but the answer is 50 degrees south of east. And let me see if I remember. I want to say I get into it. Sorry, I'm just kind of looking forward because I can't remember how I break this down. It will be part of how to draw and identify vectors lecture when you come back in. But I guess real quick, I do go into it. Into a slide here. We're going to keep on moving. Okay, so just like other vector quantities, we must put these directions in a set of brackets for our values. So this is after our values. So this is more or less just talking about when we have to identify a particular vector quantity and how we identify the direction it's moving. So as an example, here's 55 meters per second south of east, where you would have to keep in the bracket. So 50 degrees south of east, where you write out south of east, or you can have it abbreviated like I had in the slide before, where it's S of E. Now, what's important though is the order of your directions, and I'll get to that in just a bit. So we determine the heading by establishing the following. So the location the angle falls between the compass, the lead compass mark, and you have to ask yourself, what is the angle? So just using this guy right here as an example. Okay, now actually use a different color that they use. So this guy over here in the corner. So how we would use, how we would use this guy, or how we identify. So the first thing, we have to know the location that it falls between. Okay, so where does the angle fall? Does it fall over here? Does it fall in between west and our angle, or sorry, south? Oh my goodness, south and our vector here, or does it lie right here? Okay, and of course, in this picture, we know it's right here. Of course, where I just circled, it's right here. So we find the location where it falls between the compass. Okay, and this is our compass. So this would be, maybe you can't see that all that well, but north, south, east, and west. Okay, now you got to add what's the lead compass mark. So lead compass marks, and that's how I call them, I guess. I'm sure there's a better word. I haven't stumbled on it yet. But your lead compass marks are your north, south, east, and west. They're your true bearings. Okay. So what is it between, or what is it touching? So in this case, it's touching east. Okay. And because it's touching east, maybe we can think of it, or because it's touching east, east is part of this component. Now, how do we know it's 50 degrees south of east? Well, if you just listen to the way that's worded, it's 50 degrees south of east. So meaning it's like if we started, on the east bearing, and then we opened up this way, and we went south of the east bearing 50 degrees. Okay, we opened up from the south, almost like opening up a clam or open up a mussel, whatever you want, however you want to think of it. Pac-Man's mouth. So that's how we identify where that 50 lies. So that when you read this, you can say, 50 degrees, and let's see, 50 degrees if this wasn't here. 50 degrees to south of east. Definitely it's in here. It's not going to be in here, okay? It's not going to be in there because that is east of south, okay? And it's important that we know that, because when we have to identify our angles, it's super important, because if we get our angle wrong, you're going to get your vector wrong, okay? Or at least you're going to identify it incorrectly. Okay, so we've already been kind of doing this. We always need to assign a positive direction. So typically, to keep things easier in a classroom, usually north and east are your positive directions, while south and west are your negative directions. Now, that's not the case 100% of the time. There are some cases where, and for the most part, you could identify south and west if you really wanted to as the negatives. What the importance is that if you're heading one particular direction, that particular direction has to be positive, so that when you write it, or when you then travel in the opposite direction, you indicate that in the negative. Similar to what it looked like on those, velocity time graphs. On the velocity time graphs, it would look like this. So, it would look like this, and you'd have velocity here, and you have time here, right? Is that you could have it go like this and then go down. And then once it hits back here on the X, that's 0 meters per second. So it's at rest. But then when it goes down, this is like something that, it'd be like a car. It'd be like a car here moving forward. Oh my goodness, my stylus. It'd be like a car moving forward, and then reaching a point to where it begins to brake, and then brake so much that it stops, and then it goes in reverse. So you can almost think of it like if you're at like a stoplight. This particular example, it's like you're at a stoplight, and you're coming up to it. You're cruising, but then it turns red, and then you slow down, and then you come to a stop, and maybe you went over the line too far, and so then you got to put in reverse and back up so you're not over the white line. So don't give you a ticket. So but the point of talking about that is more or less the idea that you have to assign a positive direction, and we've seen where positive directions and positive vector quantities have been established, and where negative ones would be seen. Okay, and this is no different. Oh my goodness, no, I'm hitting that. Eesh. So remember the anatomy of the right triangle according to the corner of your findings. So remember, we on a right triangle we have the there's the opposite, there's the adjacent, and the hypotenuse. So the opposite and the adjacent, obviously, those will change depending upon the corner you are trying to find. Okay. However, the hypotenuse doesn't. Remember. So let's say we were looking, if we're using this guy over here as an example, if let's say we were trying to solve for this angle right here that they've already solved for, if we're trying to find theta in here, always, your hypotenuse is right here. This is your hypotenuse. But because we're looking at this angle, the opposite's going to be here and your adjacent's going to be here. Now, if we were looking up in this angle, but maybe I shouldn't have done that color. Yeah, maybe I shouldn't have. Let's keep this, let's keep this color actually. Or I'm going to do this. Watch this fancy dancy work done here. So I'm going to actually make this guy blue. So I'll be blue. Okay, so this would be opposite. This would be adjacent. Okay. And then if we were looking at this, obviously this would be opposite. This would be adjacent. And then we would have the hypotenuse here. You see, I'd made it purple. Wow. So and that would be your hypotenuse. The hypotenuse never changes. It's the longest side, the longest face of a triangle. Okay, that doesn't change. Okay, so it's important for us to remember those because we have to know those because of this great acronym, SOHCAHTOA. Okay, so remember SOHCAHTOA from trig, from hopefully you remember from geometry. It's the sine is equal to the opposite over hypotenuse. Ka is cosine equals adjacent over hypotenuse, and then TOA is tangent is equal to opposite over adjacent. Now, just the only thing that this is missing, which you'll see in the next slide, though, is just remember it's sine theta, cosine theta, tangent theta. Okay, it's your sine, the sine of your angle or of whichever particular corner that you're looking at in a triangle. Okay. So here's what I'm talking about. So remember, these are examples here in this little table. So remember, it'd be like sine of theta, sine of your theta, which in this case is 30 degrees. And this is an example that ties in with a picture down here. So the sine of 30, 1 over 2, opposite over hypotenuse, is going to be 0.5. Cosine of 30, that's going to rely on the opposite, that's going to rely on the adjacent over the hypotenuse. They, for whatever reason, have the square root of 3, which is 1.27 or 1.732. Sorry, and so they just keep it. You understand? You see, I'm confusing you if I'm continuing to talk. You see it, you understand it. We can move on. Okay, but this is a great tool because for the most part, when we're drawing vectors, we can break pretty much everything down into right triangles, which is really, really cool. Okay, so here's an example of solving for y. So the SO. Okay. So sine of theta, again, is over hypotenuse. So this is going to be sine of, and we're looking for y again. So this is going to be opposite over hypotenuse. Well, we've got the hypotenuse, we've got the theta, but we don't have the y. So what you have to do is you have to more or less just algebraically solve for this. So since 250 kilometers is dividing against the y, you just multiply it. Okay, you multiply it to both sides. So it'd be 250 kilometers times sine of 30, and you get y is equal to 125 kilometers. Now, because this is a vector, we have to remember to add the upward direction. We have to, or our direction in general. So it'd be 125 to the north. Okay, and we would do this to put this over here. My stylus, my goodness. And we do that. Let's see. Okay, and then here's an example of solving for solving in this case for x using ka. So it would be cosine times theta equals adjacent over hypotenuse. In this case, again, we don't have adjacent. That's what we're solving for, and it's literally the same thing. Okay, so it'd be cosine 30 equals x over 250, and then you just do literally the same thing. The only difference here is you've got to remember you're using cosine and not sine. Okay, and in this case, you get 216.5 kilometers. It'd be in the rightward direction or east, and again, we would write it over here, just like that. Okay, pretty simple. Okay, now let's get into these check your understanding. So determine the x and y components for the following. Now, as something that you've probably just saw in here, you're probably seeing this dr, and it says resultant. Remember, when we're working with vectors and we're working with just right triangles, resultant is the displacement. And I guess if that wasn't made clear, and resultant for the most part is the displacement, and we get into that more on when you come back to class and we do the demo and the practice with drawing vectors. The resultant is another word for the displacement. It's another word for the hypotenuse. Okay, well, not every time. I shouldn't say that. Not every time, but if you in these kinds of problems, it is. Okay, so determine the x and y components of the following. So let's write down what we know, what we don't know. So we've got a theta of 35 degrees, and we have, it looks like we've got our displacement here, our hypotenuse of this right triangle, because this is a right triangle. The displacement or the hypotenuse here is going to be, I'm going to just write h, it's 2.1 kilometers, and it says 35 degrees south of east. Okay, so this one we've got to find, let's see, the x and y. Oops, that should be red. So we don't know what the x is, we don't know what the y is, but we know how to find them. So to find our x, well, our x is up here, our y is over here. Okay, so to find our x, we've got to see where our theta is at, which is right here. Our angle is at 35 degrees. Okay, so if we want to find x, we are going to have to use adjacent over hypotenuse, which is ka. So we're going to have to use ka here. And then for y, we're going to have to use so. Okay, so let's do this guy first. So it's going to be the cosine of theta is equal to adjacent over hypotenuse, which is going to be just cosine of theta is equal to, because we don't have adjacent, we're looking for adjacent, over the 2.1 kilometers. Okay, oops, and I forgot, since we're doing that, this is now cosine of 35. And so we're going to multiply this guy on both sides, so then it's going to be cosine 35, all of that times 2.1 is equal to a adjacent, which is just the same thing as our x. In this case, if we plot this in, let's see. Okay, and it looks like we get we'll do 1.7. We'll do 1.7 kilometers. Okay, so x over here is going to be 1.7 kilometers. Now, you don't have to. Here's the thing. Okay, so now we've got two. Oh, shoot, I did not mean to do that, but that's fine. I'll just say so here, and I remember it's 1.7. So now we've got 1.7 over here. I was going to say, because you have two sides now, you could use, Pythagorean's theorem in order to find it. Arguably, though, you should use, SOHCAHTOA, because you'll get a somewhat more accurate, or you'll get a more accurate answer. So let's just finish this. So we're looking for the y, and we've got our hypotenuse is equal to 2.1 kilometers, and our theta is equal to 35. okay, degrees. And we know we've got to use sine of theta is equal to opposite over hypotenuse. So it'll be sine 35 is equal to opposite, because we don't have opposite yet. This is solving for y over here, over 2.1. We're going to do the same thing. It'll be sine times 35 times 2.1 is equal to opposite. And then that's going to be sine 35, 2.1. Looks like we get 1.2 kilometers. Okay, so this will be 1.2 kilometers. And this will be, we'll say this is to the east, and then this is to the south. Okay. And then we've solved for them. Bada bing, bada boom. Easy peasy. Okay, let's look at the next. Oh, don't do that. Don't do caption. Stop it. Oh my goodness. Also, if the audio is cracking like really bad, and if it's super loud, I apologize. I don't know what's going on, and if you've got to bear through it, I'm sorry. It did this to another video I made the other day. So again, if it is crackling, I hope it's not, but if it is, I'm really sorry. I'm trying to figure out what's wrong with my Chromebook here. So to continue on, so determine the x and the y components for the vector. Okay, so let's do that. So let's see here. Let's see. So 50 v is equal. Sorry, determine the x and y factor. So we're given this guy here. So we got to figure out this, and we got to figure out this. So here is our resultant. That is our hypotenuse. Okay. And we've got to figure out what our x and y components are. What's our x and what's our y here? So again, let's just write down what we know and what we don't know. So we know that hypotenuse is, in this time, it is velocity. So we've got 50 meters per second, and in this case, it would be 60 degrees north of west, or north of east. This would be 50 meters per second, 60 degrees north of east. Okay. We have a theta of 60. Okay. And now that pretty much this is just repeating what we did last time, I'm just going to plot in the answer for you. So for y is going to be equal to 43.3 meters per second to the north. Okay. Whereas our x is going to be 25 meters per second to the east. Okay. Pretty easy, relatively simple. Okay. We do have some challenging ones in here, so don't worry. Okay, now breaking down our vectors, continued on here. So for more context or complex problems, we can do this. We line up each vector head to tail. We break down every vector into its x and y components, and we determine the sum of the x and the y components. Okay, create the right triangle with your x and y components. So it'd be like doing this right here with this picture on the side. It'd be like we would make, a right triangle right there. It would be like making a right triangle right there as best we can, finding this angle, finding that angle, finding this angle, finding that angle. Okay. And that's what it's basically talking about. And then maybe even if you could, even doing that. That one's a little bit, I wouldn't advise that. That's a bit tricky. But you could find everything on those two. And then this guy right down here, we're going to be messing with this a little bit. That's a PhET simulator on how to, draw and make vectors and how to, find your resultant. It's actually pretty good. It's a little tricky at first, and it doesn't run as well as I'd like it to on Chromebooks, but it's not too bad. Okay, so now we get to draw some things. So an outdoor enthusiast aims a kayak northward. Okay, so aims it northward and paddles 26 meters north across a swift river that carries the kayak downstream 36 meters to the east. So 36 meters to the east. Okay. Determine the displacement. So we're finding the resultant here. We're going to find this guy right here, that green. What is our hypotenuse? Okay, what's our resultant? Okay, what's our resultant? What is our displacement? That's what we're finding here. These are all the same thing. Okay. Okay. So let's, again, just write what we know and what we don't know. Well, we know that, let's see, we know that for the x component, we know that they moved 26 meters to the north. Okay, and then the y component, we know that they moved 36 meters to the east. Now, here you could, we could just find, or we can do a number of things. So we could just find, what's it called? We could use ta here in order to find theta, okay? Well, specifically this theta right here. This is what we want to find. If you didn't see that over here, that red. If we wanted to find that angle, we could use ta, tangent over hypotenuse, or tangent is equal to, opposite over hypotenuse. We could use that. Or we could start with using Pythagorean's theorem to find our resultant. But let's go with ta first. Let's see what theta's what our theta is. So we want to find theta. And the reason, and we have to find theta because we have to tell what direction this individual is moving. Of course, we know they're moving north. They are that angled, so they're moving north of east, or sorry, they're moving east of north. Sorry. So we got to find the theta, and we got to find what angle it's moving north of east. Okay, or east of north. Goodness, east of north. Sorry, east of north, not north of east. East of north. Okay. Okay. So let's use ta. So ta is going to be this guy. So it's going to be tangent theta equal to, oh boy, this is going to be, or toa, soka toa. Why do I say ta? So toa. Oh my goodness. Toa. Jeez. It is the morning, guys. Sorry. Tangent of theta, that's theta, is equal to opposite over adjacent. So in this case, it's going to be tangent is equal to theta over, in this case, it's going to be opposite. So it's going to be 36 over 26. Okay. But now, remember, we can't divide theta or tangent. We have to have an inverse tangent. Okay. So theta is equal to inverse tangent of 36 and 26. Oh, and if I didn't tell you already, if you're not getting the same answers that I'm getting, go to mode in your calculator and set it to degree. Don't set it to radian, set it to degree. And that's probably why you're not getting the same answers I'm getting. Okay, so if you set it to degree, go to mode, and you go down to like the fourth option and you change it to degree, we should be good. So inverse tangent, and then 36 over 26, and we should get theta being 54 degrees. Okay, so theta is equal to 54 degrees. And I'm running out of time here, so I might have to cut this video short, guys, and then you'd have to, I'll give you the answers for the rest of them. You got to solve them for yourself. Okay, and then I'll post a update, like a video following the rest of the problems here, though. Okay, so 54 degrees. I didn't forget that, 54 degrees. Okay. Now we just have to find the hypotenuse. So we've got theta, so we could use theta, or we could use Pythagorean's theorem, but because we use SOHCAHTOA, probably best that we keep using SOHCAHTOA. So because we've got theta now, theta is right here, and theta is 54 degrees. And if we want to find the hypotenuse, we could just do opposite. So you could use the 26 up here. We could use SOHCAHTOA here and use opposite over hypotenuse. So we could do sine of theta is equal to opposite over hypotenuse. So that's going to be sine of 54 is equal to 26 over h. And because we are whizzes at algebra, we know we can just swap the h and the sine 54. So then it'd be h is equal to 26 over sine of 54. Okay, so and that's going to give us 26 divided by sine 54. And that's going to give us a distance of 32. Okay, 32 in this case meters. Okay, so 32 meters. So we can pretty much get rid of all this 32. So remember that 32 and 54. So then our answer would be, you could say displacement is equal to 32 meters, 54 degrees east of north. Boom. Okay. And there you have it. Okay. If there's something you still don't understand, make sure you ask me in class. Okay. Uh-oh. No, I didn't. Dude, come on, man. Sorry, guys. And now I don't know why I'm going to exit. I got to represent. Okay. And again, I'm running short on time here. So number 4, so after leaving the huddle, a receiver on a football team runs 8.5 meters to the east. Okay, so he's running 8.5 meters east, waiting for the ball to be snapped. Then he turns and abruptly runs 12 meters south. Suddenly changes directions, catches pass, and runs 13.5 meters west before being tackled. Okay, if the whole entire motion takes 7 seconds, determine the receiver's average speed and velocity. Okay, so this one, looking at the clock here. So unfortunately, I don't have enough time to finish this. So I'll just post the answer. The answers, of course, as always, are going to be in the speaker notes. Maybe actually do this one for somewhat homework. Try this one on for yourself, and we'll go over it in class when I see you guys next. Okay, so do this one, and also there should be other check your understandings we didn't get to. There's also, oh my goodness, gosh. There's also a check your understanding number 5 and number 6 and number 7. Yeah, there's no way we would have had time. Try all of these on your own. Okay. Try them all on your own, and we'll come back to them on when I see you next, whether that's Wednesday or Thursday. And we're going to go over these in class, so you have a good idea. But again, I'll put the answers in the speaker notes. Actually, no, I won't. Not for these guys. I'm not going to put them for these guys because I want you guys to work on these, and I want you to. No, I guess I will. Never mind. I keep contradicting myself. So I'll put the answers in the speaker notes. But anyway. Sorry for the confusion. Sorry that I couldn't get to all of these. Just running out of time. Took up a lot of time, and because this is some decently not complicated but busy stuff. So anyway, all right, guys. Then I will see you in the next video. Okay. See you.